I'm going to discuss the usage of the D-Wave machine on problems which are benchmark sets for a specific evaluation of the effect of pause, which have been introduced as a feature in the annealing schedule recently by D-Wave. And the work I'm going to present is in those 4 papers, which are there. I will flash them during the talk. Collaborators that helped on these calculations are from NASA, from Princeton University, from Standard Chartered, and from USC. So the outline is discussing briefly what has been the latest innovations in the computational schedules that the D-Wave machine offers us, discussing a phenomenological model of how the D-Wave machine works, which is consistent with the results of the experiments, and then see what we can say about the distribution of outputs that we get, and how this understanding port into problems which are embedded. Just a little recap. NASA has D-Wave machine since 5 years now. We upgraded to every newest generation chip. The latest one we have is 2000 qubits. Actually, 17 qubits don't work, but the rest work well. And we have the access to the all the features that have been discussed publicly by D-Wave, including the H-gain, the G-gain, I think it's called like this now, and the pauses and the reverse annealing. So we're experimenting on this, on the usage of these features from an empirical standpoint and from a theoretical standpoint. To recap, the Ising-Hamiltonian, which is implemented in the D-Wave machine as this form, as a transverse field, which starts high and gets quenched, while the problem Hamiltonian is progressively more ramped up during the anneal. Introducing a pause is nothing but just stopping the calculation at a given point in the schedule and wait a little bit. And that's about it. So before showing you results, I want to mention that many of the problems that we test on the D-Wave machine have been also simulated, if they're small enough, by Schrödinger dynamics, closed system coherent dynamics, using the parameters, the nominal parameters of the machine. And we're quite confident that the results are not explained by coherent dynamics alone. As a matter of fact, this is an example of a plot that you will see in the next slides, where you have a peak of probability if you stop the pause in a given location. I don't know if this works. Okay, doesn't matter. If you were to simulate this by Schrödinger equation, you would get the red line on top, which would be an adiabatic evolution. Clearly, the order of magnitudes of the effects we see are not explained only by coherent dynamics. So what we really need to look at is the effect of the environment to understand things. So just a disclaimer. Okay, so we're going to start looking at instances which are coming from studies which have been performed before, mainly by USC, on frustrated cluster loop problems, where we can plant a solution even if the number of qubits is very high. And this is an example of a 12-qubit Hamiltonian that we can test, and we can diagonalize even a finite transverse field. And I will use this specific Hamiltonian. This is the low-lying spectrum of the energy levels of this little instance to show some results where we understand what's going on. And we generate many random instances, and some of them are not diagonalizable because they have too many qubits. But for those that are small, we can actually know the minimum gap location and size. So what is the picture we have in mind? The picture we have in mind is that we run the annealer and we stop and pause for a certain amount of time, and then we continue, right? So what happens if you stop, in this specific instance, for example, at the beginning of the anneal, in the yellow region? Well, not much happens, because you are stuck in the ground state, and the first excited state is so high with respect to the temperature and every energy scale. And so if you stop early in the anneal, you wouldn't see any effect in the success probability. Now, what happens if you stop close to the minimum gap? Well, there you reach a situation where the density of states is rather high within your temperature energy band, and the relaxation times, the coupling to the environment, is sufficiently fast that we believe we are in a quasi-static, or as we called in different papers, isothermal regime, where you're essentially at equilibrium with the temperature of the bath during the entire evolution close to the minimum gap. So you would be a Gibbs state for a certain amount of time. Now, if you pause and you're a Gibbs state, it doesn't really matter, because you're already at equilibrium. So if you allow the system to equilibrate more, it should not have any effect. Things get interesting after the minimum gap, when the energy levels start to grow in energy, and the gap specifically, this is relative to the ground state, and the relaxation times also become slower and slower. So your equilibrium distribution starts to lag behind the instantaneous change of parameters of your Hamiltonian, and from an energetic point of view, you are substantially hotter and hotter than the thermal ground state as you go on, because you're frozen in a picture of occupation probabilities of energy levels which belong to a previous Hamiltonian. And for disordered system, this typically results in being hotter than the ground state. And so here, if you pause, then you're essentially inducing relaxation. You're allowing the system to relax and cool down, and the longer the pause you allow yourself to execute, the more heat you can dissipate. So in a way, there is an optimal location there, which is an interplay between the relaxation time, the speed at which you move, and the time you pause, that determines the best cooling that you can do to your system. And then finally, there's a region where the coupling to the bath is substantially diagonal with respect to the eigenstates in which your Hamiltonian is diagonalized. And essentially, you would have to pause an infinite amount of time to see something, or and essentially the pause is irrelevant. So this is the picture we have in mind, and the picture is essentially that we have many body time-dependent interacting open system that determines the performance of your anneal, and this is a theoretical problem which has been studied by several papers in the past, and I can't list all of them, especially the QEO ones. Many of them have been presented in this conference, so I will just refer to the posters and the other talks. But essentially, the dynamics, the performance of the machine is determined, in my opinion at least, by this delicate interplay with the incoherent effects. And if we run the D-Wave machine and we pause and we look at the best pause location that gives you the best probability, and we plot the location against the minimum gap that we can diagonalize for small instances, then we systematically see that the location of the minimum gap is always before the location of the optimal pause. So it's kind of consistent with what I said. There are some outliers, and those are instances where the minimum gap happens very, very, very late in the anneal. So, okay, so those are examples of plots that we obtained. This is for an instance of 700 qubits, so it's not, we don't have the spectrum of this instance, but we planned the solution, so we know the ground state, the classical ground state. So what we see is, if you plot in color code the energy, the excess energy with respect to the ground state, and you have the pause location on the axis, on the x-axis, and the pause duration on the y-axis, what you see is that there's a very well-definite region where you need to pause to cool down the system. And the longer you pause, the longer, the cooler the system becomes. The more energy you dissipate. And after a certain pause time, you start to have only logarithmic improvement in energy. So you're really almost at equilibrium. If you take a section of that, you really see also that if you pause longer, then the peak of probability, the peak where you get the maximum probability also shifts a little bit, which is consistent with what we said before. You have a longer pause, so you can dissipate more, so you can allow yourself to start a little bit later for the same performance of dissipation. And for all tests we did, essentially, if you plot the probability of success without pausing against the probability of success of pausing, you always want to pause. You always want to pause at the right location. So for at least these benchmark sets, which are not embedded problems, we know that the pause is a good thing. And if you increase the anneal time, so the time it takes for you to arrive at the moment where you pause, it doesn't really matter because the performance of the pause is entirely determined by the duration of the pause if you pause at the right time. So if you're looking for the location of the pause, you better try to do your test at the fast annealing the fastest annealing speed you can, because this way you determine the location of the pause and then you pause for as long as you can allow. We also did tests by rescaling the problem Hamiltonian, and this has two effects. One is increasing the effective temperature because the relative time scale, relative magnitude between the temperature and the problem Hamiltonian is being modified, and also it moves the minimum gap towards the end of the anneal if you divide the problem Hamiltonian by a factor. And what we obtain is that the location of the pause is consistently moving where the gap goes, and you're also seeing that if you divide your problem Hamiltonian by a large factor, then at this point you're essentially randomizing the problem because your coefficients are so small that intrinsic control errors and thermal fluctuation essentially determines an almost random problem. So we actually see in the scatter plot of position of the best pause and gap of the problem, we see that for the problems that are divided by a factor of 8, you have a pause location which is determined just by the thermalization dynamics and not by the problem instance. And the gap is substantially random because the problem is random. So we think we understand what's going on here. Another interesting result is looking at the statistics of the output of the D-Wave machine. And what we see here is that if we look at the distribution that we obtain when we pause at the best pause location that we find, if we look at that specific statistics, well, then it is fitting rather well. This is a KL divergence color code plot. A Boltzmann distribution, which is at the transverse field corresponding to the pause location, where you paused, and the temperature corresponding to the nominal temperature of the machine. So it seems like somehow that we are statistically sampling from the problem Hamiltonian, which corresponds to the pause that where we stop. However, we could also fit well the problem, the statistics with the classical Boltzmann distribution at a higher temperature. which is also useful for sampling applications. And what we show in the paper is also that the larger the problem, the more true it is that the distribution is substantially a classical Boltzmann distribution. And we do some statistics about that. So the takeaway of this particular problem study is that it is always convenient to pause if you're wanting to increase the probability of reaching the ground state or a low energy state. And for disordered problems, it seems that you're always wanting to pause after the minimum gap, and that the distribution of output, if you pause at the right location, or the best possible location, is fitting a Boltzmann distribution of the classical problem that you're studying. Now, what happens if you pause in embedded problems, in problems which are application problems? So embedding is the procedure for which you take an Ising Hamiltonian that you want to study, and you represent in the chimera chip of the D-Wave machine by using ferromagnetic substructures, which represents your logical variables. And in this particular case, you have other parameters that are somewhat free, to some extent at least, which, for example, represent the ferromagnetic couplings of these vertex models that represents your logical variables. And all of this modifies the energy landscape of the problem and introduce all sorts of effects, which have been studied in several papers. Now, for the first study I show, we use a fully connected problem, which we know how to embed efficiently from the design, the early design ideas of the D-Wave machines. And we know that we require overhead of a square. Basically, every logical variable is represented by a number of physical variables which scales with the problem size. And I'm going to present results from this paper, which is not online yet, but has been accepted yesterday at the SIGCOMM conference, so you can actually download it from that link. It will be on the archive probably on Monday. And it's about wireless decoding. It's essentially a problem that we studied with Princeton University, where we are looking at the maximum likelihood optimization, where we're trying to understand what's the most likely signal that we received from a signal which has been sent through a noisy channel. And there are a lot of details there, and it's a problem which is substantially computationally intractable at scale, and is a fully connected QUBO for several encodings. And the embedding of this case allows up to 64 fully connected variables, because that's the chip size we have, and that means 40 users in this multi-input, multi-output wireless formalism. The details are on the papers. For us, we need to know that what we're looking at is this time not the probability of success. We're looking at the time to solution. As a matter of fact, in the paper we look at the time to bit error rate, which is a different metric, but for the purpose of this talk, we can consider it as time to solution. So this is the only plot I'm going to show about this paper. There are many in the paper, but I want to show that if we pause, first, we get the best results. Second, we can set the pause location and duration independently from the ferromagnetic couplings and the annealing time of the test instances. So those are plots that show studies where we scanned over different pause locations, and different colors represent medians over instance sets for different ferromagnetic couplings of the embedding. And what we see is that there is a best ferromagnetic coupling, and there is a best pause location, but the dip, the peak of probability is essentially the same independently from the ferromagnetic couplings you set. Now, you might want to find the best ferromagnetic coupling and the best pause location, but those are independent problems, which is good for application purposes. And in this particular case, we want to go as fast as possible and to do as little pause as possible, but that is because of the specific problem. For other problems, it could be different. We have another evidence of the fact that we want to pause also in embedded problems from the Convergent Aeronautics Solution project of NASA. There was a poster by Zhui Wang yesterday where we studied the weighted Steiner tree problem, and which was related to network wireless drone network optimization. And we see also a probability of success peak in embedded instance. This time they're not fully connected. They're using the D-Wave heuristic if you pause at the right location for the right time. And the same kind of arguments apply for reverse annealing, which I'm not going to present for lack of time, but there is a paper related to finance optimization where we pause in a reverse annealing mode by using a hybrid algorithm, and we obtain as well that the pause location can be independently determined with respect to the J-ferro, the ferromagnetic coupling, and the annealing time. So another evidence of that. And we find also good results with respect to the state of art in this particular paper, which is published. And I'm going to conclude now just saying that we're really continuing this effort at NASA, and we welcome collaborations and applications to work with us. And I want to advertise in the last second or so that you should write me if you want to be part of a mailing list, which is starting on July 15, where we will essentially curate a digest of the archive every month. It will be a monthly, so it will not be spam. By us, where we essentially are going to feature all the papers that appear in the archive that we believe have an impact in the near term for quantum computing community. Not only annealing will be a good part of it, but also gate model. Thank you very much.
Questions?
Okay, so if I understand correctly, there is only a final region where it's relevant if you pause. Okay, I mean there is only this region. So if you pause once, is it useless to pause again after you have done one pause?
So is your question, is it useful to pause twice?
Yes, in the region.
We're looking at that. We have up to 4 pauses in our annealing schedule, given by D-Wave. So far, for the problems with a single minimum gap and so on that we studied, we don't see any smart strategy for which we would want to pause multiple times. I believe that with reverse annealing, we might start to have the opportunity to pause multiple times, also because with reverse annealing, you meet the gap twice in certain situations.
So it seems like you said the final distribution depends on where you have paused, right?
Correct.
So if you pause twice, which is it the first or the second pause that determines?
I do not have statistics on the output of the double pause case.
Okay.
Is there a way to determine the position of the optimal pause without creating statistics, maybe in an analytical way?
I believe that the same reasonings that have been discussed in other talks during the conference could apply to try to estimate where the optimal pause location is. So trying to figure out by some non-spectral method based on estimating the curvature or other sort of things where to pause. But no, so far we do not have a precise analytical guidance.
Because if you would have to create statistics to find the optimal position, you would have solved the problem already anyway, right?
Yes. But so far what I would recommend is, from a very purely practitioner empirical point of view, to do fast scans and see any drop in the average energy that you get, and probably be guided by this to commit on a region.
Hi, Davide. Thanks. That was a great talk. So you spent a lot of time talking about pause position, but it seems you were pretty consistent about pause width. And did I hear you say that it kind of it didn't matter much, or that it's kind of always obvious what the width of the pause should be?
Well, the general region is obvious because of the schedule of the D-Wave machine, in a way, because you can't be too far away from the center of the schedule. But the distance from the minimum gap, it's not a priori clear. I think it's really an interplay between the density of state, not only the minimum gap, but also the structure of the low-lying energy, excited energies, excited states of the instance. So, bottom line, we know that we need to scan between 0.3 and 0.5 in the S variable of the annealing scale, but we don't really know where. And it could be very narrow if you decide to pause very little. So you need to find it. Well, if you pause long time, then you allow yourself to a larger region.
Yeah, it seems like there might be a sweet spot there, a trade-off that might also be worth looking for.
There's certainly a trade-off there.
Yeah.
So the pause is certainly has a really dramatic effect, which is great. But I wonder, based on your theoretical understanding of what's going on, whether this is a quantum or a classical effect. And to be more precise about that, suppose you had a classical algorithm mimicking the annealing, like spin vector Monte Carlo, and you introduced a pause there. Do you know if you would see the same effect, or is it different?
We do have some simulations going on with some people in your group, but I do not feel confident to answer one way or another this question. I think that the effect we see are dominated by classical physics. However, some of the timescales that we see, which reflects in the pause duration effect, and are determined by effects that probably relate to incoherent tunneling, and they have a quantum component into it. Now, whether this is providing a speed up with respect to thermal dynamics, it's not clear. But I think that this is going to be a question that we need to answer the next year or so.
Is it possible to say that in an ideal machine, pausing will be irrelevant? In a sense that ideal meaning totally noiseless.
No, it will not be irrelevant because.
So, and why is that? Because if there's no noise coupling between the energy levels, why would it cool down the system if you pause it?
But irrelevant means.
In a sense that you don't need to pause, and no, you would just.
It might not be particularly useful to pause in a fully coherent system governed by Schrödinger dynamics, but it will be very problem dependent in that case, because you would have anyway oscillations depending to the.
So it has additional functionality in addition to actually cooling it. You're saying?
I think pausing is a tool that is not particularly genius. It's just like a way to modify the schedule and try to drive your system where you want to go. And the nice thing for us is that thermalization is a computationally useful effect, because we are so governed by dissipative dynamics that it becomes a useful tool. Now, if you are so at weak coupling to the environment, and you engineer your schedule in such a way that you do not have a lot of excited state in the game, you probably don't want to pause a lot, I suppose.
Thank you.